Let me have the pleasure of introducing Dr. Shankar Rajasekaran. He's a subject matter expert on air cleaning and contamination control engineering. He has over 31 years of experience in this industry. He's a certified professional from National Air Filtration Association USA and also from the Clean Room Testing Certification Board International from the UK. He's trained on air filter testing from Harvard School of Public Health, USA. He has professional education on the aerosol and particle measurements from University of Minnesota in the USA. He is currently the technical director at Impact Filters from Chennai, which manufactures particulate and gas phase air cleaning products. He is the chair of ISHRE Technical Group for Air Filters, ISHRE Standards Committee, which is a standard for performance testing of air filters. He's the panel member for the Bureau of Indian Standards, the Government of India, for refrigeration and air conditioning. Let me hand over the mic to Mr. Shankar to present his chapter. Thank you.
Thank you, everyone. And it's my pleasure to be here, giving out this talk and sharing information on this important topic. So we'll spend the next 30, 35, 40 odd minutes to be discussing about the clean air standards and what are these standards based on? What is the concept on which it is based on? Because it's always important to understand the concept on which a standard is made rather than just getting to know the numbers. So we will move. But before we get in, what was the golden word, golden sentence that this lady said? She said, the hospital is a place where it should do the sick no harm. It's very important. But quite unfortunately, when the patients come into a hospital, they can actually get harmed at times inadvertently because of medical errors, physical injuries because of falls, slips, etc., accidents during patient handling and other fire accidents and other sort of accidents, and more so of in later days, the hospital acquired infections, which by statistics in India is reasonably quite high. So as engineers, do we have a role to play in controlling hospital acquired infections? Yes, absolutely we do. Because more and more hospitals are getting air conditioned and mechanical air conditioning and ventilation has become the norm. And we have moved much from those days where we had the hospitals with open windows as for the wards and at times even for the theaters once upon a time, as the previous speaker was also mentioning several decades back. But today, more and more hospitals are becoming high-rise buildings because of land shortage, scarcity, and air conditioning is becoming a must. And as a result of which, the infections that the patients can acquire in a hospital is also on the rise. So the target for an air conditioning system or a ventilation system, other than creating a comfort kind of a situation, is also to help in reducing the occurrence of nosocomial infections. So how are standards actually made? We look at a particular risk. So the risk has to be identified. If something is not standardized, what is the risk? Then we assess the risk and we measure the risk. It's measured and assessed. Then we look at the procedures or the process which can mitigate these identified risks. And then we will also be looking at the methods with which we can validate the risk mitigation procedures. And based on all this, the standard is developed. So the standard will have to address or talk about the risks that are involved. It will have to look at the procedures that are required or the systems that are required to be in place, and how can the systems be tested and validated to ensure that they are in proper working condition. All these things have to be taken into account when standards are developed. So what would we be touching today? we would be touching about the concept of infection prevention from an engineering angle, some common standards applicable for clean air environments in hospitals. We'll talk about operating rooms and we'll talk about isolation rooms. We talk about challenges in providing the clean air, and we'll just spend a small amount of time talking about a particular case study, a small case study. So the concept of infection prevention, looking at it from the engineering angle. We know about the chain of infection. For an infection to happen, there has to be an agent and there has to be a reservoir where the agent will multiply. We need a portal of exit from the agent source. Then we need a mode of transmission. That's where we come in. Then there has to be a portal of entry and a susceptibility for the host. If the chain is broken, so this is what? The reservoirs could be human, animal, or environmental reservoirs. Since we are bothered about talking about air conditioning, we are interested in environmental reservoirs. How environmental reservoirs can be reduced, or how they can be, prevented from affecting the much critical areas like ICUs, operating rooms, isolation rooms, etc., etc. Of course, the portals of agent exit and the mode of transmission. It could be direct contact, vehicle-borne, airborne, or vector-borne. Again, since we are talking about air conditioning, we are concerned about the airborne mode of transmission, and we need to ensure that we take adequate steps to prevent, block, or break the chain of infection through the airborne mode. Because we said if we break it at any point, then the chain stops. Of course, these things are there anyway. So the contaminant pathway, if it is disconnected, then the infection is prevented. It is also avoided if an agent dose is insufficient to trigger an infection. This is extremely important. So it is not necessary that the infectious agent has to be completely absent. It is also okay, of course, barring certain procedures, invasive procedures like surgical procedures, barring a few of them. For the other areas of the hospital, even a dilution of air, diluting the concentration of the infectious agents is good enough to prevent contamination and infection from happening. This is because infections occur on account of pathogens entering the human body in a manner that overcomes or compromises the human system. So if the concentration is less, then we can stay protected. So dilution is important as well. So we look at infection prevention in engineering terms. We look at it as we want to control contaminants moving into the occupied parts of the building. Yes, more so with critical procedure areas. So what are the basic concepts? Of course, we need to limit the source, personnel protocols and procedural protocols like, zoning and other kind of applications. We talk about physical barriers, primary barriers which are physical. We talk about anti-rooms and graded isolation. We have the secondary barriers, which is very important, which is going to be very important for especially the ultrafine particles and the very small bacteria and viruses, by maintaining pressure differentials. Because even a closed room, a room with a closed door, will have gaps and crevices through which the contaminants or the infectious agents can leak inside. So we do that by we prevent contamination and infection by using pressure differentials in critical areas. We use airflow patterns. We make the air to move in a particular way so that the most critical part of the procedure is given the maximum amount of protection. When I'm talking about purging and scavenging, because not only is the environment or the air that we bring from outside having infectious agents, but there could be internally generated also, because of so many people who are and so many people doing so many activities inside the space. There could be internally generated contaminants also, which needs to be scavenged and removed in real time. Otherwise, that concentration will keep on building up. So you will have to keep removing them in real time basis as and when they get emitted or generated. And then, of course, we also spoke a little in the earlier slide, we spoke about dilution. That is by supplying clean air and then ensuring that the contaminants are getting diluted. So we need to apply as many as possible in this that we see in the screen, so that we will be able to have maximum control on infection spread. So what are the functional requirements of a HVAC system used in critical areas? Of course, we maintain temperature and relative humidity requirements. That's for comfort as well as from the infection prevention angle. Introduce adequate amount of contamination-free outside air, that is for dilution of the several gaseous pollutants that could be generated inside. Minimize addition of contaminants to very low levels through multi-stage filtration. And remove internally generated contaminants effectively by providing streamlined airflow over critical areas without eddies or swirls as much as possible. This is pretty much what Mr. Vinod was raising as a question. What happens, because we are expected to have streamlined airflows so that the eddies won't form, and the eddies and swirls negatively affect the removal of contaminants. So that is actually a big challenge that we face in all the places. Suitable positioning of supply and return air points. That's very, very important. If we keep it in such a way that the supply air, instead of coming into the room, gets bypassed and a part of it goes directly into the return air point, then it's not done its job. We have not taken the benefit out of that. So we'll have to look at the positioning and look at the adequate number of air changes. How many air changes to provide? So these are all the functional requirements of HVAC system, HVAC system used in a critical area, and each one of them has to be taken care. And of course, we have to control the ingress and egress of contaminants from or to surrounding areas by building adequate positive or negative pressures. We will look into that also. So these are all the functional requirements. We will have to build it into the system in one way or the other. So air movement. Air needs to keep continuously moving. If the air gets stratified, it becomes a place where the contaminants will build up. So contamination-free moving air in a clean room is the most important functional element. Uniform dilution and scavenging action cannot happen effectively unless air moves in a particular pattern in the entire room. So higher magnitude of air movement results in faster removal of contaminants. So if you look at a table here which shows as we keep increasing the air changes per hour, the removal time, the time required for removal to 99% efficiency keeps on falling down. And this is for achieving a removal of 99.9% efficiency. When we talk about air changes, it means we are recirculating the air with this many number of air changes through adequate level of filtration and completely removing the particulate matter from it. So we do filtration of at different levels, most typically a HEPA filter, which we will be talking about in the slides to come. So this is what you are likely to look at. You're likely to get something like we normally have between in a surgical procedure. We're not likely to have anywhere between about 18 to 20 minutes between two surgical procedures, or at the maximum say about half an hour. Nothing. We are anyway somewhere in this band. Between 14 to 28 minutes is normally the time these days we get between two procedures. And you look at the time that is required for a 99% removal, and the theater to come back to its steady condition of aseptic nature takes something like about 20 minutes. So 20 air changes, it takes something about 14 minutes. And if you want 99.9% removal, at 20 air changes, it takes something like about 21 minutes. And this is more or less what we are looking at, around 20 minutes. If the theater can get ready for the next procedure, that's good enough. So the air changes are extremely important. So we talk about pressurization. So there are two possibilities. One is we can positively pressurize a room by in a way where we supply larger quantity of supply air and take out a lesser quantity of return air from the room, whereby the extra air exfiltrates from the room, and the exfiltration of the air, the velocity, exfiltration velocity, takes care of the preventing the contaminants from coming inside. The other case is a negative pressurization, where we don't want the contaminants from the room to go to the other parts of the hospital. Very much the case like we have in the scenario of COVID these days. These are at a lower pressure with respect to the surroundings, and the air infiltrates into the room. Here, the exhaust volume, air volume, will be larger than the supply air volume. And there will be an exhaust into it. There will be an exhaust separately provided so that the negative pressure is taken care of. So we have been using, everybody uses HEPA filters these days. So what is the efficiency of a HEPA filter? We normally have the habit of talking about it in terms of particle size at 0.3 micrometers. But then what happens to the particles which are lesser than 0.3 micrometers? That's an important question. More so, typically these days, the COVID scenario, we have seen that the COVID virus has a size of somewhere about 100 to 200 nanometers, to give it in a slightly broader this thing. So the question was like, if this virus was there, will the HEPA filter be able to remove it? So that was a question. So if you look at the efficiency curve versus particle size of a HEPA filter, it's a U-shaped curve, which means there is a bottom point at a particular value for a particular given particle size. And for any other size which could be lower or greater than that particular size, the efficiency will only be better. So if we know the efficiency at this size, whatever is the efficiency at this size, then that means for any other particle size, even if it is 0.1 micrometers or 0.05 micrometers, the efficiency will only be better. This is a characteristic of any HEPA filter, irrespective of the make. As long as the filter is doing its job and working in its correct way, the filter will have to behave like this, because it's a characteristic of the technology. So that's the reason. And if you look at the normal kind of HEPA filters that we use in the operating rooms, the lowest point, the bottom point, normally happens at around 0.15 to 0.2 microns, that band, and it normally gives you it is supposed to give you an efficiency of minimum of 99.95% at that minimum point. So if you're looking at 0.3 micron size, which we normally talk about, it will be much higher than 99.95. So if you look at this chart, they aerosolize several types of organisms, these being the virus, bacteria, and the fungal spores. They, depending on the color, as you can see it. And we all know that the fungal spores are quite big and viruses are quite small and things like that. So, So as we keep, the size becomes larger and larger, and this side it's smaller and smaller. So as we look at this, the curve is again very similar to this, and they have given in ppm, parts per million. as the penetration. So penetration of 400 ppm is 0.04%, which means it is 99.96% efficiency. So this bottom point I'm talking about, this 400, this bottom point, more or less matches with the engineering calculations that we get. So we can say that the HEPA filter will provide an efficiency of about 99.95% for all microorganisms, including most of the virus, bacteria, and fungal organisms. So this becomes our, greatest weapon, Brahmastra, it becomes in our fight against the infection spread and contamination control. So that's about the concepts for contamination prevention, infection prevention. So we'll now look at some of the standards applicable for clean air environments in hospitals. So the first one that we very normally use because of ease of usage, the simplicity of the standard, as also it's not too simple, it covers a reasonably large spectrum of information, but it's quite simple and easy to follow. For that reason, this standard is quite popularly followed. It's called as the ASHRAE standard 170, the ventilation of healthcare facilities. It's practical and simple to use standard. It provides technical information regarding pressure, temperature, RH, filtration level required, etc. for almost all areas of the hospital, starting right from OP areas to the lab to the autopsy rooms, the entire CSSD, cafeteria, procedure rooms, surgical rooms. It covers everything. It provides clear-cut information. One another place where you can find all this information is what the earlier speaking was referring to as the FGI guidelines, facilities guidance, FGI guidelines, or the AIA, American Institute of Architects. And the other document where you can find this is the Environmental Infection Control Guidelines of CDC, the Center for Disease Control. But this one provides you, ASHRAE standard provides you in a very simple and easy to understand manner. It covers isolation areas quite nicely, and it clearly tells about where the position, this standard doesn't say. The standard comes along with another book which is called as the ASHRAE handbook, guidebook for healthcare facilities and clinics. There it talks about how it can be, I'm sharing some pictures from that book where it clearly talks about how the supply and return air can be positioned in isolation areas. It provides guidance on planning, construction, and startup. So, and the recommended operation and maintenance procedures is given as a separate appendix. So it reasonably covers this whole this thing, and I would recommend that every facility engineer in a hospital needs to be having this as a guidance book, and but of course, quite unfortunately, it is not available on free download. If you will have to buy it as a PDF, it can be bought. It's not very expensive. You can buy it. The next one, which is typically my personal choice, is the standard called HTM 0301 parts A and B. HTM is the Healthcare Technical Memorandum of the UK. This document is from UK. The earlier one was from ASHRAE US. This one is from UK. As you can, this is one thing which really gets down to the details. It has a separate section. The HTM 0301 is exclusively for HVAC systems, and specialized ventilation systems is covered in a large portion. This document is almost like about, parts A and B put together is almost like 200 pages of in-depth information with all kinds of information about how a testing and validation has to be performed also. No other standards talk about how a testing has to be done, but this standards very clearly tells how a testing can be done. It gives options for different kinds of layouts for a surgical block, etc., etc. So it's a very good standard to follow. Fortunately for us, this is available on free download. I am sharing the link in one of the slides that follows. So it's a very prescriptive kind of standard, wherein it very clearly says this is what you should be doing, this is how much you should be doing, this is why you should be doing. It's absolutely prescriptive. Extensive details about the design concept, testing and validation. Where testing and validation most important, like the other documents, standards don't talk about it, but they are very, very clear. The other standards normally refer you to some other testing standard, but here everything is given within the same document only. And it covers the requirements for air handling units. It covers the entire air distribution network. The ASHRAE document does not cover it. The ASHRAE standard 170 does not cover air handling units. And it specifically covers specialized ventilation systems which are used in operating rooms and ICUs. Specialized ventilation systems cover the ultra clean ventilation systems for operating rooms in an extremely fine detail. The next standard, as we all know, is the NABH, guidelines for operation theaters, which most of us do follow. And this is also available, I'm sure you all know, it's available on free download. This is the simplest of the three standards to follow when it comes to air conditioning. But it covers just the operation theaters. There is no mention about anything. Nor do they talk about the air handling units or the ducting or anything with reference to the operation theaters. They talk more so with the indoor conditions that are required and the equipments that we will have to use, not much so about the specification or the details about the equipments that are there. But the truth of the matter is, it's quite a flexible standard in that it allows several practical deviations, which is also necessary when there are a lot of smaller hospitals wishing to upgrade. This acts as a motivating factor. Instead of creating a huge financial burden, this allows some practical deviations, which is in one direct, looking at it in one way is good. But of course, the standard will nevertheless need to evolve and come on par with the international standards on all fronts. It provides simple tips for operation and maintenance and clearly mentions the type of tests which have to be done, but does not mention how it is to be done. But it clearly specifies the type of tests that we should do and what is the frequency that it has to be done. Right? Quite clear about it. So I'm providing the links for download or purchase. The NABH, the ASHRAE, and the HTM. The links are here. We can copy from. You can Google it and find it. So we'll now just go to the operating rooms specifically. We very commonly call laminar flow theaters, modular theaters. We
Shankar.
use these words very commonly nowadays. We had the turbulent flow systems earlier, and now most of the hospitals are moving towards what we call a unidirectional airflow systems. It's typically not to be called as a laminar in the true engineering meaning, but it's to be called a unidirectional flow system. And it is the same one that the HTM calls it as an ultra clean ventilation system. So I've given some characteristics of the unidirectional flow and the turbulent flow system. It's quite self-explanatory. The main part of this is that near constant velocity, this is a very, very important part of the, This is a very important part. The velocity has to be constant. It can't fluctuate, number one. It has to be low phase velocity. And it is to be high level of velocity uniformity. So these three things are the most important aspects of a unidirectional airflow system. Low phase velocity, high level of velocity uniformity, and near constant velocity. Whereas in a turbulent flow system, it will be just the opposite. And if you look at the last point, It is used in very critical and clean surgeries, the last point, whereas the turbulent flow system will be utilized in not so clean surgeries like a gastrointestinal tract surgery or what do you call OG, gynecology related surgeries, things like that. Whereas this one will be used in all the clean surgery, like cardiac, neuro and ortho and all that stuff, transplant, organ transplant, etc. etc. This one cleanses the air by action of dilution and contaminant transport away from the critical area. This one cleanses the air by action of dilution only. That's the main difference. So I am giving the definition of what is unidirectional flow, because very unfortunately, sorry to say this, many of the operating rooms which are supposed to be working as a unidirectional airflow do not work as a unidirectional airflow theater for several reasons, of course. So I thought I better put down what should be the what would be the definition. And it says there are two standards which talk about what is a definition, engineering definition for airflow. And this ISO standard talks about velocity variation within plus or minus 10% from the range, from the average, when we talk across the supply air diffuser. And when you look at this standard, it talks about an airflow that has a velocity relative standard deviation of less than 15%. If you do it rightly, you can get it actually less than 5% relative standard deviation. And that will be a really nicely performing operation theater. And if you look at good values of site measurements, average particle concentrations measured on the operating table, that's the important word. The HTM is the only of the three that we talked about. The HTM is the standard that talks about measurement of particle counts on the operating table. The NABH talks about particle concentrations on the supply air grill and not on the table. But the critical area is on the operating table. And if you look at that, this in a good OR with unidirectional airflow, this is the kind of particle concentrations that you will get for every cubic foot. And this is what is the allowed limit as per the standard. And this is what you will get in a turbulently ventilated OR. A good turbulently ventilated OR, I'm saying. So you can look at the benefits of using a unidirectional airflow system. But if it is not done correctly, installed and tested correctly, it creates more harm than good, which we will be seeing. If you look at the ASHRAE study, they talk about the single large diffuser and they talk about the medium multiple diffuser array. So and you can look at the area here, area in square feet. This is the area of the diffuser. As the diffuser size increases, the colony forming units, that is the availability of microbial load on the operating table, keeps on reducing at SLD1, which is 57 square feet in area. When operated at 50 feet per minute, it becomes 0. So we're talking about CFU per meter cube. And at 30 feet per minute, it's just got 2. And most of the theaters nowadays have a 8x8, which is 64 square feet, or they have 8x6, which is 48 square feet, pretty much close to this, I would say. So if you operate it anywhere above 30 feet per minute, we are likely to get a very low microbial CFUs per meter cube on the operating table. Thereby the aseptic nature and the sterility of the air will be maintained. So I'm giving some information about how to achieve this unidirectional airflow and what are the diffusers to use. I'm not going to be reading through it. I'll move through this. It's quite self-explanatory in nature. So I'm also giving how to measure how many points are required. I can just take velocity at one point and move away, but that's not allowed. The different standards talk about different requirements for measurement of unidirectional airflow, how to measure and how to this thing. If you look at HTM, the most toughest one to do the testing. It will be very, very tough and takes a long time to do the test as per HTM. We're talking about target values for velocity. The HTM, it is 0.38 meter per second or 2 meter from the supply diffuser and 0.2 meter per second, which is close to about 40 feet per minute at 1 meter from the floor level. And they're saying it's got to be only plus or minus 6% variation is allowed. NABH talks about 25 to 35 feet per minute. But this value was earlier 90 to 120. They have now been revised. ASHRAE also talks about 25 to 35 FPM velocity, but this is all at the supply grill. HTM is the only thing which says at 1 meter from the floor level and 2 meters from the supply diffuser, what values will have to be there. That's why I said the HTM standard becomes very, very specific and very, particular. So these are the allowable microbial limits. 0.5 CFU at the terminal diffuser and less than 10 CFU on the operating table. The NABH does not talk about particle microbial values. It talks only about the particles, and it says less than 100 particles of 0.5 microns in size for every cubic foot of sampled air at the diffuser. So we'll quickly come to isolation room. They're talking about whether the patient is to be protected from the environment or the environment needs to be protected from the patient. So we're talking about airborne infection isolation rooms, which is what we are now talking about. After the COVID, this has become very popular. The air has to be a negative pressure room, and the return air will have to be sucked from close to exhaust air, and return air, as you can see here, will have to be sucked from close to the patient, and the supply air will have to be provided from the entry part of the room. So there will be a sweeping action towards the patient so that the patient's aerosols are not getting transported outside. So this table gives you some information about, since it is isolation, I thought I would give some values because it might be important these days. How many air changes are required? And in a negative pressure isolation room, anti-room is mandatory. We have to have a separate anti-room. So it's characterized by negative pressure, clean to dirty airflow direction. Anti-room is mandatory. Exhausts are to be vented out safely at a suitable height, or they can be recirculated back through HEPA filters. It's very clear. So you can't recirculate the air from an AII room back into the air conditioning system without the use of HEPA filters. And it uses constant volume, air volume systems. A PE protected environment system isolation room is what is used for transplant surgeries and other critical ICUs and surgical ICUs, where the patient, or in the case of organ transplant, also in the case of oncology rooms, for patients having immune deficiency conditions. So we look at the air being supplied over the patient and the air moving out of the room. So this will be a positive pressure room where the patient will be given a bathing of washed by a stream of ultra clean air through HEPA filters, and then it will leave the room so that the patient will be protected from the contaminants from outside. So we look at some challenges in providing clean air now. Of course, we all knew the grills, ducts, air handling units, filters, all these things need to be taken care of. There have been cases where, not because of some water pipeline or something getting ruptured or something like that, but because of the problems in pressure differentials, air from above the false ceiling mixing with the operating room environment through the light pendant or the surgical pendant shafts. We have had cases of, we have several places seen water condensation. So, and there have been several cases where we have seen high microbial load in the diffuser screen of your unidirectional airflow system. These things are really, wrong in the sense those equipments which are supposed to be providing the benefits of clean air themselves become the culprits. So as engineers, we need to look at such things don't happen. So we'll discuss some of the classical problems that we experience at site. So damaged filters or improper filter installation. Improper fitment of laminar flow diffusers. This is a most important thing. The reason being, we said if the velocity uniformity is affected, then the laminarity is lost. If the laminarity is lost, it loses the capability to transport the contaminant away. So if you don't fit the laminar diffusers properly and in a leak-free manner, what happens is there is difference in velocity that happens, because of which the very purpose of providing a laminar diffuser is lost. And the worst part is, because it is directly above the patient, if it is going to bring in some contamination inside, it is going to directly dump it onto the patient. Whereas in a turbulent system, the diffuser was not right above the patient. So by the time the contaminant comes into contact with the patient, it would have got diluted. That's why using a unidirectional airflow system, when not done properly, increases infection rates in some hospitals. Static charge, using the wrong kind of material, thereby static charge build up on the synthetic diffuser screen, and thereby that becomes a possibility for the contaminations to be attracted and built up there. Many places we have seen contaminated terminal filters and improper insulation of the surgical pendant chute, so which leads to water dripping on the surgical table. Shutting off the air handling system during the non-use hours of the OR is a common problem that we face, but that results in contamination buildup, and this is one of the reasons why the terminal filters get contaminated. Once the cases are over, if we open up the theaters and we switch off the air conditioning system, then all the dirt goes and gets loaded up on the exit side of the terminal filters, as a result of which it builds up and it contaminates the filters. Many times the water stagnation in the air handling units because of drain piping, condensate piping not being blocked. Air leak in the air handling units. Relative humidity much higher than what is prescribed. Lack of return ducting. This is a big problem everywhere. ASHRAE very clearly says that whichever place there is a need to maintain a differential pressure requirement, return ducting has to be there. You can't take sealing return. Improper sealing of the surgical pendant chute, I think it's a repeat. Duct leakage. Duct leakage more than energy wastage. It is looked at a different. See, imagine an operating room where you have HEPA filters at the terminal and the duct leaks above the false ceiling. From there is every possibility that the unfiltered air can infiltrate into the operating room through any gaps or small cracks that can be there in the false ceiling at the corners, and thereby the operation theater sterility would be compromised. Improper positioning of return and sizing return air suction points, improper air balancing. Many times I see this, that the pressure is not getting built up because of improper air balancing. And mostly inadequate testing methods. Thereby, we don't detect the flaws. So what are the points to be considered? All return points to be ducted. Do not allow for crevices. All interior surfaces must be hard cleanable. Adequate precautions during maintenance retrofit renovation, because maintenance retrofit renovation is a time which actually spreads contamination around, and there are clear-cut documents for this. Some hospitals have even set up guidelines wherein they classify the kind of maintenance work into several categories, and the type of patient rooms where they are doing, the risk to the patient room, the risk to the patient, and based on this matrix, a suitable procedure or a strategy is adopted. Using of tacky mats, using of pus boxes, and ensuring that the or leak free, ducts are leak free. So we can use lots of parametric measurements for testing for air cleanliness. Minimum these are required: temperature, RH, supply air, velocity, uniformity, total exchange rate, fresh air change rate, positive pressure, installed filter test, leakage test, particle concentration, flow visualization, and microbiological sample. So yeah, this is a case study wherein prior to HVAC correction and after HVAC correction in a neurosurgical theater, look at the kind of for 363 surgeries that were considered, there were 71 central neurosystem infection post-surgical, and there were CSF, cerebrospinal fluid infection, on 7 patients, which accounts to 19.6% and 1.9%. After the HVAC correction, 623 surgeries were taken into consideration, and just 4 had central neurosystem infection and none on CSF. So you can look at the reduction from 19.6% all the way down to 0.6%, and this has been documented in this this particular article. It was done in Chennai only, and there are several such articles which are available, and they very clearly said the sole apparent change involves the air filtration system inside the neurosurgical operating rooms. This environmental change occurred during the 5 months between the 2 studies. So it's very clear that the proper HVAC system would be very, very helpful. So this is a conclusion. Contamination control through engineering systems are sure shot protection and helps reduce infection transmission and infection spread. Properly designed HVAC system is a 24/7 tool for fighting against infections in a healthcare facility. And unidirectional airflow systems provide an aseptic environment in critical zone only when designed, installed, and tested properly. In the absence of above, these systems cause more harm than good.
Thank you, Shankar. Thank you very much. We have overshot the time, but definitely it was very interesting, very much informative. Yeah, the question from Vishal Bansal: if we see an increase in surgical site infections, how can we be pinpoint towards air conditioning as a causative factor? And what needs to be done if we have excluded all other aspects that can possibly cause increase in SS site?
Okay. The only solution is to conduct. This is one common problem that always happens. Normally, when the SSI increases, the OT staff, the staff nurses are asked to do cleaning better, and then swabs are taken, active air sampling is done, and again the microbiology will come back with a positive this thing, and then they will say air conditioning is a problem at one point of time. The only way to rule out this is by completely testing the system for proper performance in the absence of surgeries, and ensure that the engineering part is ruled out. Having said that, SSI is not only due to mechanical interventions like facility related matters. It is more so to do with several other aspects also. Back table contamination is a very, very common thing which is being considered these days. Number of door openings and door opening frequencies has been documented as a very big causative factor. I was talking to a GI, a theater where it was used for kidney transplant in one of the hospitals, and I was shocked when I heard that during the course of a surgery in 1 hour, they opened the door something like 30-35 times. So these things have been documented. So there is no way for the theater to stabilize itself. The other main reason is about the layout, the architectural layout of the OT block. And what we normally consider as a sterile corridor is not actually a sterile corridor, because most of the places it does not have air conditioning, or even if it has only comfort air conditioning. So these are multiple factors that we need to look out. And once we can remove all the engineering side factors, then I think we will have to leave it to the medical team, because it could be back table contamination, it could be CSSD related. I have even had an experience that it was a microbiology testing related problem, because of which they were continuously saying that the cultures are positive, positive, positive again and again, after repeated interventions by the facilities team.
Okay, sir. Thank you very much. That was the right answer, and I think you touched upon the topic of the number of times the OT doors are opened during a surgery, which normally just gets unnoticed, and the problems start rising in the theaters. I think we should end up this session right now. Thank you, Shankar sir, for all this time and the energy that you have spent for explaining on this chapter.